am Abel Rochberger, Chief Engineer Services with GTC Control Solutions in Hawthorne, New York. With GTC since 2014, I've been doing field service, customer training, presentations at user groups, and now we're doing remote service and remote presentations due to this pandemic. I live in Buenos Aires, Argentina, and we've been quarantined since March 20th. Oh, it's been an experience. I have an agreement with my barber that I met in 1979. He does not do turbine controls and I don't do haircuts. I believe in the power of mind, and I've been trying to not allow my hair grow. I've been not very successful here, but here, as you can see, I've been extremely successful. So more or less we're even. What are we going to discuss today? We will be presenting the single point of failure, two case studies, one about redundant thermocouples and another one about redundant speed sensor. It is about an LM unit, aeroderivative unit, but depicts dramatically the importance of detecting single point of failures. Then we will discuss TIL implementations. Two TILs in special, because they apply to all gas turbines. TIL 1524, when one exhaust TC fails high, a particular case of a single point of failure that resulted in a TIL, and then TIL 1275, excessive fuel during startup, the P2 pressure control. As a bonus track, we will discuss very shortly the difference between average versus core-by-core LVDT calibration. The Mark 6 and the Mark 6E went back to the Mark 4 style of calibration, doing it core-by-core by themselves. The Mark 5 does not do that. So that's the Mark 5 that requires special attention. GTC was founded in 2001. And we have been ISO certified since 2008. Regarding GE controls, we do turbine excitation, LCI, generator, all the family of GE controls for turbines, steam or gas. And then we also care about the Bentley Nevada, the vibration sensors, DGP, and Chemetron is not a GE product, but is usually associated with the fire protection systems of GE gas turbines. In the services part, we provide support for forced outages, emergencies, field service, training, and lately, remote field service and remote training. Let's take a quick view at our service center in Hawthorne, New York. You can see all the panels. Those panels are energized, and that's where we do the testing, the final testing of the cars before they're packed and shipped. It's been in operation since the end of 2015, and you see at the right, at the top, there is like a monitor. That's where we track every single order that's processed. Green is good, yellow is and red perhaps should have been shipped today or yesterday or a couple of days ago. So we try to keep it at green. This is a panoramic view of our warehouse. In the warehouse, you can see to the right shelves and shelves of parts, and on the left you see lined up a lot of panels. Those are panels that have been decommissioned by customers, and we acquire them and strip the parts, the useful parts from the panel, process them, and put them back in service as remanufactured parts to help our customers maintain the equipment that have been declared by the OEM either discontinued or obsolete. They keep running the units like nothing, and they have been in service for 20, 30, 40 years, even 50 years. We see again the items to discuss. The ambient temperature thermocouple differential that causes a not ready to start. Then the speed pickup that spikes and trips the unit during start, and then the TIL implementations, TIL 1524 and TIL 1275. And this is the end of this introduction. Now we're going into the specific discussion of each item. We're going to talk about the single point of failures and the TILs. First case of the single point of failure. It's about 4 units that have disagreement of the inlet ambient temperature thermocouples located at the inlet filter house. So they were readily accessible, very easy to get to them, and the customer complaint was we have non-ready to start condition, and we troubleshooted to these ambient temperature thermocouples. There are 3 of them. They are volted thermocouples. But what happened is that we need a no high differential condition to be able to start the unit. So the ready to start depends on a no high differential condition of these 3 thermocouples. So we arrived to a 2-part disposition. But let's first review how we arrived to that 2-part disposition. This is a picture of the thermocouples that were giving trouble. The one on the left is the one on the west side. The one on the right is the one on the east side of the unit. As you can see, the boxes are pretty similar in size, so we can use them to scale the distance, and seems like the one on the west is much closer to the wall than the one on the picture on the right. That also means that, and explains why they were seeing this high differential. On these lazy, sunny afternoons, the sun was hitting the west side much more than the east side that was in the shade already, and that caused a differential. There's a third thermocouple in the center, so she doesn't care. One way or the other, she's okay. So how can we solve this high differential? We looked at it and said, well, look, you are checking the difference between the thermocouples, and if 2 have a high difference between the highest and the lowest, the differential is too high, you have this problem, you have this high differential. So let's consider the typical ambient temperatures that you'll find on this location and set those as limits and say, if my thermocouple is reading between these limits, my thermocouple is okay. If my thermocouple is reading beyond these limits, that thermocouple is not okay and I will not consider it. And creating those detections for each thermocouple, and then a sequence that says, okay, 2 out of 3 are okay, they're not reading crazy ambient temperatures, then that means that we have a good value for the ambient temperature, we do not have a high differential, and we can start the unit. If 2 out of 3 thermocouples are outside the limits, then the permissive to start is not satisfied, because now the control system is saying, wait, 2 of your inlet thermocouples are not reading correctly. You cannot start the unit in this condition because this is a critical parameter for your DLN calculations. So with a very simple software modification, we solve the problem. Since then they had very successful starts all the time. At least the problem of thermocouple is gone, and that was a single point of failure condition, because with one hot thermocouple, or is too close to the wall, they could not start the unit. The second part disposition was, we recommended you can relocate the thermocouples towards the center of the inlet filter house, and let's say put them like 2 or 3 feet away from the center thermocouple to each side, because that's basically what you want, an average ambient temperature in the filter house without actually reading the temperature of the wall. This is how we solve this case. Customer never had another complaint about this issue anymore. Let's go now to the second case. This is related to an LM unit, LM5000. But we chose this case to present these single point of failure conditions because it's really a perfect example of what can be done when you have dual element, not triple element, and one of those 2 elements goes crazy. The systems usually consider that one of the devices fail low. That, for instance, if they stop reading, the reading that you get is low. But we have seen devices can fail high. LVDTs can fail high, thermocouples can fail high, and speed pickups can fail high, as in this case. The LM5000 has 2 speed pickups per shaft. It's a multi-shaft unit. The original sequencing has a high select block that determines the speed of the unit and also calculates a high differential. The 2 speed pickups are not reading outside specified limit. One fail high detector trips the unit. This is a single point of failure. In fact, what happened, the story goes like this. The customer was starting the unit, no problems. All of a sudden, one of the 2 speed pickups reaches 128%, which is the max scale for speed, if you're familiar with controls. And when reading 128% speed, the protective system says, oh, wait a minute, we have an overspeed trip. And the unit was just cranking. The actual speed of the unit was about 28%. So they had a spike, they tripped. And after the trip, they restarted again. They had to wait, go through a purchase. They lost like an hour and again tripped. And eventually, one of these attempts, the unit will survive the start and go through the normal sequence. That was completely unacceptable because they were called to duty and they were not on time online. And you know, guys, what happens when you're not on time online. So when I saw this, I said, well, there is another block, a not very well-known block, that has the I/O check, input-output check. And the input-output block selects the input that is working okay. So if one is out of the limits, high and low limits, it says this one is not okay and gives an alarm saying that failed, that one failed. Then it also calculates the differential between the two and also detects if the second failed. So if both failed, you're out of luck. You cannot run. If one failed, it will consider that one and continue with the sequence normally because you have one good sensor, and it will tell you the other one was rejected. You have an alarm, and it will also give you a high differential. So the operator will know what happened. And if both work okay, both are within the acceptable limits of operation, the block will calculate the average of the two. In speed pickups, the average is basically the value they read because they're really very, very close to one another. But for instance, in lube oil or bearing metal thermocouples, the average of the 2 thermocouples may give a better indication of what the actual temperature is than just taking the high value. And with this, we conclude the discussion of the 2 single point of failure cases that we wanted to present. An earth, please. Name the land that moves to the rhythm of geothermal, aeolian, and combustion energy. The answer is Boogie Wonderland by Earth, Wind, and Fire. We will discuss 2 TILs, TILs 1524 and 1275, and then a bonus track. 1524 deals with the case of a single point of failure, and it avoids it. Thermocouples, as we mentioned before, can fail high. And in the case of the exhaust thermocouples, one exhaust thermocouple failing high would cause a high exhaust spread trip. That's a very annoying situation. So this TIL, what it does is uses the second highest exhaust thermocouple to calculate the spread and avoids the situation. So if the first thermocouple that fails high will not cause a high exhaust spread trip. But if you leave one fail high and you do not fix that, and a second thermocouple fails high, then yes, you will still have the high exhaust spread trip. So the recommendation is if one thermocouple fails high in operation and you have this TIL implemented already, disconnect that high exhaust thermocouple, the one that has failed high, and then you still have a better chance of limping out to the next outage and do the exchange of the thermocouple. if the thermocouple cannot be exchanged online. The standard software typically uses a simulation that is part of the sequencing, automated simulation, but with all the customers that we uh, discussed this TIL and implemented the TIL for them, they agreed with a very simple modification. We removed the automated testing part of the sequencing because it affects also the startup sequencing. It has a permissive that you're not in testing to allow the startup. And we removed that completely and did a simulation of the sequencing, as I will explain in a couple of minutes. This is how the screen looks after we implemented the TIL. You see that we also have created some sequencing there to allow the testing, enable testing without forcing signals that go everywhere. And what we did is we took a spare thermocouple terminal board, this is for a Mark V, and installed it with jumpers and with millivolt sources. You will need basically 2 millivolt sources to implement the testing. And because once it's tested at your site, in your unit, you don't ever need to test that sequencing again. Once it proved that it's working, it'll work exactly the same time always. We finished this very simple discussion of this TIL. Please let us know if you have any questions about implementing TIL 1524. TIL 1275. The protection against high P2 pressure control during startup, and then the control of the pressure in high and low conditions in normal operation. But the main thing is avoiding excessive fuel or high P2 pressure during startup. This TIL also makes sure that the pressure, P2 pressure, is below 6 psi before the unit starts. What is P2 pressure? P2 pressure is the pressure between the first valve in the gas fuel module, the speed ratio valve, and the gas control valves. That cavity between these two valves holds P2 pressure. In order to have a safe start, the P2 pressure cannot be above 6 psi before the start. The speed ratio valve is not tight shut off. The valve is not designed to be tight shut off. It has a classification, an ANSI class 4 classification, while the valve upstream of the gas fuel module, which is usually not supplied by the OEM, is customer responsibility. That block valve must be tight shut off, ANSI class 6, and also a vent to make sure that the space between the block valve and the speed ratio valve is vented, has no gas, and therefore we make sure that the pressure downstream of the speed ratio valve will be less than 6 psi during startup. So you need an automated tight shut off block valve and vent, ANSI class 6 or better, smart sequencing of the gas and vent valves, and determination of adequate time constants. How did we come up to that? So the first customer we implemented this TIL for, we did the modifications, started the unit, and we had 60 psi P2 pressure, and the speed ratio valve opened 8%. That tripped the unit on the protection. We realized that we had to do something so the valve would not open that much. P2 pressure will be 25 psi, the theoretical value, and the unit would not trip during startup because of the TIL we just installed. That was like chasing our tails. So this is what we did. We staggered the valves safely so there will be no gas going into the unit without spark plugs, the igniters on. And the sequencing created first opens the gas control valve, the stem on the right, then you'll hear a whoosh, which is the block valve opening, and last, the speed ratio valve opening. And in this case, after the modification, the P2 pressure was exactly 25 psi, and the speed ratio valve opened only 0.8%. Let's see the video. So You see, we did the staggering of these valves and the results were phenomenal. The customer was so happy when he saw the results. I mean, he said this unit never started so smoothly. All four flame detectors detected flame within 8 seconds into the firing timer. He looked like a kid that opened the back door to the backyard on Christmas Day and found out that Santa left him a pony. He was beaming. Let's play the video again. Pay attention to the first stem on the right. That's the control valve opening when the spark plugs already started. Then you hear the whoosh of the gas coming in after the block valve. And finally, a very small movement on the stem of the left, which is the speed ratio valve. And with this, we finalize the presentation of our TIL 1275. We finally arrived to the last slide, the bonus track. When in Mark V units, you calculate the average of the results of the calibration and input that average to all three cores, you're introducing an error. This is what's happening. Each core reads its own voltage because it has its own physical components, capacitors, resistors, the things that read the voltage coming from the LVDT, and translates that with an offset and a gain into a position. And you can see here, if you use the average, each core will calculate its own position. And they're sometimes quite different, perhaps even 1% difference or more. When you do the core by core calibration, this is what you're doing. And it's obviously different. The voltage interpreted by each core is converted by its own gain and its own offset into the same position for all three cores. And it's amazing the difference. The position interpreted by each core is almost exactly the same, with a 0.1% difference between cores. This is a problem particular to the Mark V, because Mark IV does core by core calibration automatically, and GE went back to the core by core calibration in the Mark VI and the Mark VI-C, basically using the Mark IV style of calibration of LVDT feedback. We can go into more detail of how to do proper calibrations of all the devices for all the panels, and we have developed very interesting procedures to do this calibration and have very precise results. Thank you very much for your attention. This is the end of our presentation. Please call us if you have any questions.